You start by letting your mind rest on the simple idea that the night sky is not still. The stars above you look calm, but they sit inside a universe that changes slowly and steadily. When astronomers first tried to understand how far away galaxies were, they expected a quiet cosmos, a place where everything stayed more or less in the same arrangement. What they found instead was movement, so gentle it takes millions of years to show its shape, yet real enough to measure with careful instruments. You follow that early search as if stepping into a clear, quiet observatory, where each observation brings you closer to understanding how the universe behaves. You picture the large telescopes of the early 20th century, built to gather faint light from galaxies far beyond the Milky Way. Astronomers looked closely at these distant systems, measuring brightness, comparing colors, and studying subtle features in the light that reached Earth. One of the most important clues came from something called redshift. When the light from a galaxy stretches toward longer wavelengths, it appears slightly redder than expected. This shift happens because the space between the galaxy and the observer grows over time. As space expands, the wavelength of the traveling light expands with it. You hold the idea gently, noticing that the light itself records the stretching of space. Edwin Hubble, working at Mount Wilson Observatory, compared these redshifts with measurements of how far away certain galaxies were. Distance was not easy to determine, but astronomers used special kinds of stars called standard candles, objects with known brightness. By comparing the true brightness of these stars to how bright they appeared from Earth, scientists estimated the distance to their galaxies. When these distances were plotted against the redshifts, a clear relation appeared. Galaxies farther away showed greater redshift. This meant that distant galaxies moved away faster. You let that simple pattern settle in your thoughts, appreciating how a straight line in a graph revealed something profound about all of space. The discovery carried a quiet clarity. It said that the universe was not static. It was expanding. The galaxies were not sailing through space like ships moving across an ocean. Instead, the space between them was stretching. Imagine dots drawn on a balloon that slowly inflates. The dots do not move on their own, and yet the distance between them grows. This simple analogy helps you approach a concept that happens on the largest scales known. It does not change the internal structure of galaxies or the bonds between stars inside them. It acts across the vast spaces between clusters of galaxies, where gravity is too weak to hold everything together. You ease into the idea that expansion is not something you could feel if you drifted through space. It is slow, so slow that only by measuring light that has traveled millions or billions of years can the change be seen. The expansion rate becomes visible only when comparing distances across cosmic time. The universe grows by tiny amounts in human terms, but those small steps accumulate over its immense lifetime. This perspective lets you rest in the understanding that cosmic change is patient. As more precise instruments were built, the measurements became clearer. Telescopes above Earth's atmosphere observed galaxies in wavelengths that ground-based telescopes could not easily detect. Light from ultraviolet to infrared added more detail to the story. Each new observation confirmed the overall pattern. Galaxies in every direction drifted away. The redshift was not limited to one region or one cluster. It was a universal effect, suggesting that the expansion happened everywhere, not from a single central point. You reflect on how this finding reshaped how scientists think about the cosmos. A static universe would eventually collapse under gravity unless an opposing force held it stable. But an expanding universe showed a different balance, one guided by the fabric of spacetime itself. The equations of general relativity proposed by Albert Einstein already contained the possibility that space could stretch or contract. With Hubble's measurements, the mathematical framework and the observational evidence connected. The universe was dynamic, and its large-scale behavior followed measurable patterns. To understand the expansion more fully, astronomers needed accurate distances. Standard candles became essential tools. Cepheid variable stars, which pulse in brightness in a predictable way, allowed scientists to measure nearby galaxies accurately. For greater distances, Type Ia supernovae served as more powerful markers. These supernovae occur in a specific, well-understood way, giving astronomers a consistent brightness to calibrate. By comparing observed brightness to expected luminosity, they could calculate immense distances with remarkable precision. You imagine how each calibrated measurement makes the map of the universe more detailed, like adding carefully placed guide stars in the darkness. These methods help you see the expansion not as a simple concept but as something deeply rooted in evidence. The light that reaches Earth carries a history written into its wavelength. Redshift measurements show how long the light has traveled and how much the universe has stretched during that time. When astronomers compare thousands of such measurements, a coherent picture emerges. The farther back in time we look, the younger and more compact the universe appears. Clumps of galaxies sit closer together, and structures are less spread out. You sense how observations across billions of years allow scientists to reconstruct a slow, smooth motion that would otherwise be invisible. Another way scientists study expansion is by examining large-scale patterns in the distribution of galaxies. Over time, gravity draws matter together into clusters and filaments, while expansion stretches the space between these structures. These competing influences leave subtle imprints, like faint ripples, in the arrangement of galaxies. By measuring these patterns, astronomers learn how fast the universe expanded at different times in its history. These data gently confirm the view first uncovered by Hubble. The universe continues to expand, and that expansion shapes everything on the largest scales. You rest in the understanding that expansion affects distance but not the internal structure of stable systems. The Milky Way does not grow with cosmic expansion. Your solar system remains bound to the sun. Atoms stay the same size. Expansion is noticeable only across vast stretches of intergalactic space where gravity is too weak to hold matter tightly. This helps you feel the scale of what astronomers measure, reminding you that the universe behaves differently on different levels. As you absorb these ideas, you find a quiet comfort in how the evidence comes from light that has traveled so far. Each photon carries information from a distant place and a distant time. Together, these countless signals form a consistent description of a universe that changes gradually. The idea that space stretches becomes less mysterious when seen through the lens of direct observation and careful reasoning. You finish with a soft awareness that the expansion is only the beginning of understanding how the universe evolves. Light from distant galaxies still carries more clues about what drives this slow growth and how it may change over unimaginable spans of time. You begin by settling into the quiet idea that the universe, already vast and expanding, does something even more surprising. Instead of slowing down over time, the expansion speeds up. This discovery did not come from speculation or imagination but from light, measured carefully across decades. You follow the gentle, steady path of astronomers as they search the sky for clues that could reveal how the cosmos behaves on the largest scales. In the 1990s, two independent research teams studied distant type Ia supernovae to measure the expansion rate. These supernovae occur when a white dwarf in a binary system accumulates enough material to ignite a runaway nuclear reaction. Because the physical process that triggers the explosion is well understood, the resulting brightness is remarkably consistent. This consistency lets astronomers use type Ia supernovae as standard candles for great distances. You picture the faint light of these explosions traveling for billions of years before reaching Earth, carrying a clear record of how far they have come. The scientists aimed to find out whether the expansion of the universe was slowing due to gravity. Massive objects attract each other, so the expectation was simple. Over time, the expansion should decelerate. By measuring extremely distant supernovae, astronomers could look back into a younger universe and compare its expansion rate to what exists now. You rest in the idea that observing faraway objects is like observing history, because the light shows the universe as it was when the photons began their journey. When the measurements were analyzed, something unexpected appeared. The distant supernovae looked dimmer than anticipated. If they were farther away than predicted, then the universe must have expanded more rapidly during the light's travel. This meant that the expansion was accelerating, not slowing. You imagine the researchers checking their instruments, recalibrating their data, and repeating their analysis, wanting to be certain before accepting such a surprising conclusion. The results were confirmed by both teams, using independent methods and separate datasets. The dimness of the supernovae was not an artifact of dust, instrument error, or mistaken assumptions. Each possible explanation was tested methodically and ruled out. The only consistent interpretation was that the expansion rate increased over time. This finding did not rely on a single observation but on dozens of carefully measured supernovae across different parts of the sky. To describe this acceleration, scientists used the term dark energy. The name does not imply a substance filling space or a force acting with intention. It simply refers to the observed behavior of spacetime. Something about the structure of the universe causes expansion to accelerate. Because the effect is uniform across space and does not clump like matter, it behaves differently from anything previously measured. You hold the idea gently, understanding that dark energy is a description of a phenomenon, not a claim about an unseen material. The discovery aligned with a term already present in Einstein's equations of general relativity: the cosmological constant. Einstein originally introduced it to maintain a static universe and later removed it when expansion was discovered. The accelerating universe made the cosmological constant relevant again, not as a mathematical convenience but as a measured property of spacetime. You reflect on how theories sometimes wait quietly for evidence, becoming useful when observations reach the needed precision. The supernova results alone were persuasive, but astronomers wanted broader confirmation. Additional lines of evidence came from the cosmic microwave background, the faint afterglow of the early universe. Tiny temperature variations in this background radiation encode the geometry and large-scale behavior of spacetime. When scientists compared the observed patterns with theoretical models, the data supported a universe dominated by a form of energy with negative pressure, something that drives acceleration. You imagine the delicate fluctuations mapped by satellites, each pixel contributing a small piece to a larger cosmic picture. Another independent source of evidence came from measurements of large-scale structure. Galaxies do not distribute randomly through space. They form patterns shaped by gravity, expansion, and the initial conditions of the early cosmos. As scientists mapped galaxy surveys covering millions of systems, they found that the growth rate of these structures matched the predictions of an accelerating universe. These observations formed yet another consistent narrative. Expansion does not slow as distances increase. It grows stronger. Even with these confirmations, astronomers treated the findings with caution. They tested alternative explanations, such as modifications to gravity or variations in supernova brightness over time. Each alternative had to fit all available data, and none did so as well as the model that included dark energy. You find comfort in the care taken, the patience of researchers who know that extraordinary claims require careful, repeated testing from multiple directions. You rest in the understanding that dark energy does not act on local scales. It does not pull on atoms or planets or stars. It influences the expansion of space itself, becoming noticeable only across very large distances. On scales of galaxies or solar systems, gravity overwhelms the expansion, making local structures stable. But across the immense stretches between galaxy clusters, dark energy becomes significant, shaping how the universe evolves. The measured effect of dark energy is expressed by a parameter called W, the equation of state parameter. It describes the relationship between pressure and energy density. For a cosmological constant, W equals -1. Observations so far show that West is extremely close to this value, though small uncertainties remain. These uncertainties motivate ongoing research, as each refinement helps scientists better understand how spacetime behaves. You sense the quiet effort behind these measurements, knowing that precision takes time and patient observation. To measure W, astronomers continue to gather data from supernovae, galaxy clusters, gravitational lensing, and cosmic background radiation. Instruments such as the James Webb Space Telescope and ground-based observatories provide sharper images and more accurate distances. These improving measurements help reduce uncertainties and refine the models describing the universe's acceleration. You appreciate how each new dataset feels like another piece placed softly onto a growing picture, making the overall shape clearer. You allow the idea of dark energy to settle without imagining it as anything mysterious. It is a term researchers use to describe an observed acceleration. The universe behaves in a way that indicates an influence with negative pressure, consistent with a cosmological constant or a similar effect. This behavior is established through independent evidence from supernovae, background radiation, and large-scale structures. You understand that science proceeds by observing, modeling, testing, and revising, not by assuming or storytelling. The concept becomes calmer when you think of it as a measurable feature of spacetime. Just as gravity shapes how objects move, dark energy shapes how distances between galaxies change. It does not act suddenly or violently. It works gradually over billions of years, guiding the expansion in a steady way. This slow, large-scale behavior allows scientists to study it through light that has crossed the universe since its earliest ages. You relax into the realization that dark energy is not about prediction or fear. It is about understanding the universe through consistent evidence. Each method of measurement reinforces the same conclusion. The expansion is accelerating, and that acceleration defines the universe's long-term behavior. You hold the thought lightly, appreciating how calm and steady the scientific process can be. As your thoughts quiet, you reflect on how the discovery of acceleration reshapes the way scientists explore the cosmos. Light from distant supernovae still reaches Earth, carrying signals of how expansion behaves across time. These signals point toward deeper questions about the nature of spacetime, questions that continue to guide careful observations that reach farther into the universe's history. You stand at the edge of a great invisible ocean, not made of water, not made of air, but made of something far stranger. This ocean has no color, no temperature, no motion you can feel. Yet it surrounds you, fills the cosmos, and quietly reshapes everything it touches. You breathe slowly, letting your mind settle, and begin to sense the faint rhythm of the universe beneath its surface. This is dark energy, not a substance you can scoop in your hands, not a force you can point to, but a property woven deep into the fabric of spacetime itself. You imagine spacetime as a vast sheet stretching in every direction, smooth and silent. Stars rest on it like lanterns set upon a taut cloth, their gravity pulling down and forming gentle curves. For a moment, the universe feels peaceful, suspended in perfect balance. But then you notice something else, an upward push, subtle and persistent, rising from beneath the sheet. It is as if the fabric itself wants to lift, to expand, to create space where none existed before. That upward push is dark energy, a quiet pressure embedded in the geometry of the cosmos. You picture galaxies like islands scattered across a wide, dark sea. At first they drift slowly apart, their motions governed by ancient gravity laid down during the universe's earliest moments. But as you watch, the drifting accelerates. The islands pull away faster and faster, as though an unseen tide is growing stronger beneath them. This acceleration is the signature of dark energy, the evidence that reveals its presence even when all else remains unknowable. You cannot see dark energy directly, but you can watch how it pushes the cosmos outward, stretching the distances between galaxies with every passing moment. You close your eyes and feel the expansion, not as motion but as a soft, spreading sensation. It is gentle, almost tender, but relentless. Space itself is growing. Every moment, more room appears between clusters of galaxies, between superclusters, between the grand filaments that form the cosmic web. The universe does not expand into anything. It expands from itself, as though creation is an ongoing act. Dark energy is the quiet engine that fuels this growth. To understand it better, you imagine yourself shrinking to a scale far smaller than atoms. You drift down into the empty space between particles. At first it seems utterly void, just silent nothingness. But then you sense a faint hum, a whisper of activity. Even in the smallest regions of vacuum, energy flickers in and out of existence. This vacuum energy, predicted by quantum theory, may be related to dark energy. Perhaps the universe is filled with this background hum, a baseline of energy that exerts gentle pressure everywhere. The exact nature remains uncertain, but the idea helps you grasp how something so strange can be so universal. Now you zoom outward again, rising past atoms, molecules, planets, and stars until you stand once more in the vastness of the cosmic web. You watch how dark energy influences structure on the largest scales. Gravity tries to pull matter together, gathering galaxies into clusters and clusters into grand formations that stretch for millions of light-years. Dark energy, meanwhile, works in the opposite direction, pushing against this gathering, pulling everything apart. The result is a delicate tension, a cosmic dance between attraction and repulsion. In the early universe, gravity dominated. Galaxies formed, stars ignited, planets took shape. But as time passed and distances grew larger, dark energy's influence increased. Now, billions of years later, the balance has shifted. Dark energy drives the universe forward, faster each moment, while gravity tries to hold on to what it can. Where matter is dense, gravity still wins. But in the enormous voids between galaxy clusters, dark energy stretches the emptiness wider and wider. You take a slow breath and imagine this stretching on human scales. If dark energy suddenly increased, galaxies would rush away from each other so quickly that the night sky would go dark. If it vanished, everything would slow, perhaps even collapse one day into cosmic contraction. But the universe does not behave so dramatically. Instead, dark energy works with remarkable steadiness, like a constant whisper guiding the rhythm of expansion. Its strength today is the same as it was billions of years ago, a consistent pressure shaping the fate of all things. You begin to wonder what dark energy means for the future. You picture a remote era trillions of years from now, when galaxies have drifted so far apart that their light can no longer reach one another. The cosmos becomes a scattering of lonely islands in an ever-widening sea. Stars burn out, galaxies fade, but expansion continues. Even then, dark energy persists. Its influence grows more dramatic as matter thins out and distances stretch further. You watch as the universe becomes quiet, not crushed or torn, but endlessly expanding into colder and darker domains. Then you imagine another possibility. That dark energy may change. Perhaps its strength will evolve, growing or diminishing across unimaginable timescales. If it grows too strong, the universe might face a catastrophic future, the so-called Big Rip, where galaxies, stars, planets, and even atoms are torn apart by runaway expansion. If it weakens, gravity may one day reclaim dominance, slowing the expansion until it halts, and maybe even reverses. These scenarios are speculative, yet they reveal just how much influence dark energy wields over the future of all existence. Yet for now, the universe remains calm. Dark energy acts with gentle consistency, guiding the expansion without violence. You take another slow breath and let this idea settle. The cosmos is shaped not by loud explosions or violent events alone, but by quiet, persistent influences that operate everywhere, always. Dark energy is one of these influences, silent, patient, and all-pervading. You turn your attention to spacetime itself. Instead of imagining it as a sheet, you now picture it as a vast, flexible grid stretching in all directions. Each line of the grid marks a tiny region of space, and each moment adds a new layer of time. Dark energy subtly alters the spacing of this grid. With each passing moment, the intervals grow slightly larger. New space appears between the lines, not because anything forces them apart, but because the geometry of the universe demands it. Dark energy is embedded in the equations that describe this geometry. It is written into the curvature of spacetime, shaping the cosmic story at its deepest level. As you observe the grid, you notice something serene about this process. Expansion does not tear or break spacetime. It is a natural unfolding, like petals opening in slow motion. You sense the tranquility of this motion. It happens everywhere yet disturbs nothing locally. Planets do not drift apart. Stars remain bound. Galaxies stay whole. Expansion works only over enormous distances, beyond the reach of local gravity. This distinction allows the universe to remain stable on small scales while shifting dramatically on vast scales. Now you drift farther until the cosmic web fades into a soft glow, leaving you with a mental picture of the entire universe at once. You see its earliest moments, its present era, and its far future woven together. Through all of these stages, dark energy plays its subtle role, guiding the universe through expansion, shaping the distances between galaxies, and setting the rhythm of cosmic evolution. You breathe slowly, feeling the vastness settle into your thoughts. Dark energy may be mysterious, but its influence is clear. It stretches space-time, accelerates expansion, and shapes the ultimate fate of the cosmos. It is the quiet sculptor of the universe, working with patience and precision. And as you stand in the midst of this cosmic unfolding, you realize something simple yet profound. The universe is not just expanding outward. It is expanding within you too, in understanding, in awareness, in calm. Dark energy may be invisible, but its story brings a kind of clarity, a soft reminder that even the faintest forces can shape the grandest destinies. You sit quietly with the concept of dark energy still lingering in your thoughts, its gentle pressure expanding the universe with a calm persistence. Now you turn toward a more extreme possibility, one that cosmologists study not because it is dramatic or frightening, but because it emerges naturally from the mathematics. This is the Big Rip, a theoretical future in which dark energy grows stronger over time, eventually overpowering every binding force in the cosmos. You breathe slowly, reminding yourself that this is not fantasy, nor prophecy, but a scientific framework built on equations, observations, and models. You begin by imagining the universe not as static but as a system evolving through its expansion factor, a parameter that tracks how distances change with time. In standard cosmology, dark energy has an equation of state parameter, written as W, that describes how its pressure relates to its energy density. You pause to let this sink in. Pressure and density together determine how dark energy drives expansion. The value of W becomes a key to understanding the universe's fate. You hear the simple rule whispered by cosmologists. If W equals -1, dark energy acts like a constant, the same today as tomorrow. This is the familiar lambda of the lambda CDM model, the standard picture where expansion accelerates but remains gentle enough that galaxies, stars, and atoms stay intact. Then you move to the more exotic idea. If W-1, dark energy density increases with time. This is where the Big Rip lives. The equations tell you that when W falls below -1, the vacuum energy grows, pushing harder as the universe expands. Instead of thinning out, it amplifies. You imagine a feedback loop where expansion stretches space, this stretching increases the density of dark energy, and the increased density accelerates the stretching even more. The effect compounds, a quiet multiplication that unfolds across billions of years. You let the numbers guide you. For W just slightly below -1, say -1.02 or -1.05, the process is slow. The universe continues to expand gently for an extremely long time. Only after trillions or quadrillions of years would dark energy become strong enough to unbind galaxies or disrupt structures. But if W were significantly below -1, the timeline could theoretically shorten. Still, even in these models, the times involved dwarf the age of the Sun, the Earth, and human history by unimaginable margins. The important idea settles calmly. The Big Rip is not triggered by sudden destruction but by the mathematics of an evolving energy density. Cosmologists study it not because they expect it, but because the equations naturally allow for it when W dips below a certain threshold. You picture a graph of the scale factor of the universe, a smooth curve rising slowly at first, then steepening as dark energy dominates. In the Big Rip scenario, the curve bends upward more sharply, eventually approaching infinity in finite time. This mathematical divergence signals the ultimate moment when every physical structure succumbs to expansion. You don't feel fear in this vision, only curiosity, as though reading a calm, precise description of a distant phenomenon. Next, you turn to the underlying physics. You recall that energy density normally dilutes as the universe expands. Radiation spreads out and loses intensity. Matter becomes less dense as space grows. But dark energy behaves differently. For W-1, its density increases as the universe expands, a counterintuitive property that emerges from the very fabric of the equations. You imagine a universe where expansion does not weaken the vacuum but enriches it, creating more of the same mysterious energy that drives the acceleration. Cosmologists call this form of dark energy phantom energy. The name sounds dramatic, but the concept is strictly mathematical, an equation of state parameter less than -1. You sit with this term, realizing that nothing supernatural is implied. It is merely a label for a pressure so negative that it causes an accelerating acceleration. You trace the consequences step by step. First, galaxies recede from one another more rapidly. Then, in trillions of years, galaxy clusters lose gravitational cohesion. Later, galaxies themselves disperse, their stars no longer bound to shared centers. Eventually, solar systems would unbind as well. Finally, if the process continued unchecked, even molecules and atoms would be torn apart by the runaway expansion. Each stage corresponds to a specific point in the evolution of the scale factor, calculated from models that use the value of W to map the future into precise mathematical intervals. But you remind yourself, this is only one theoretical outcome. It depends entirely on the value of W, which remains uncertain. Current measurements place West extremely close to -1, with uncertainties that still allow room for different futures. The Big Rip is possible only if W is consistently and significantly less than -1, a result not yet supported by data. You breathe easily, knowing that cosmology deals with probabilities, not certainties. You reflect on why scientists take the Big Rip seriously at all. It is not because they expect it to happen soon, or even within any meaningful cosmic timeframe. They study it because it reveals how sensitive the universe's future is to the properties of dark energy. By exploring extreme models, cosmologists understand how even tiny deviations from W equals -1 lead to vastly different long-term outcomes. The Big Rip illustrates the role of pressure, density, and the geometry of spacetime in shaping cosmic evolution. Now you picture a simple equation. Rho is proportional to A-3, 1 plus W, where Rho is the dark energy density and A is the scale factor. This equation condenses the concept into a single expression. For W equals -1, the exponent becomes 0, and density remains constant. For W -1, the exponent becomes positive, and density grows as the universe expands. You let the elegance of this relationship settle into your mind. A small change in a symbol, a shift below -1, creates an entirely new type of cosmic evolution. As you sit with this, you appreciate that the Big Rip scenario is not an imaginative story but a rigorous possibility rooted in models of general relativity. It is a legitimate branch on the tree of cosmological futures, not the trunk, but still firmly attached. You feel the quiet precision in the way cosmologists examine these branches, evaluating each one with data, observations, and theoretical reasoning. You observe how measuring W becomes crucial. The closer it is to -1, the more stable and gentle the future appears. The further below -1 it falls, the more dramatic the Big Rip scenario becomes. Yet even then, the timescales remain enormous. The universe would have to evolve through many epochs far beyond anything human civilizations, planets, or even stars could witness. This leads you to a calming realization. The Big Rip is a future so distant that it becomes more of a mathematical horizon than a physical concern. Its value lies not in prediction but in understanding. It shows how cosmological models can describe multiple fates depending on the input parameters. It demonstrates how sensitive the universe's trajectory is to the behavior of dark energy. And it illustrates how science embraces even extreme possibilities when they arise naturally from equations. You take a final breath and let the ideas settle. The Big Rip is not a threat. It is a framework, a way of thinking about the universe through the lens of physics. It reminds you that cosmic futures are determined not by imagination but by measurable quantities. W, expansion, energy density, and geometry weave together to form the tapestry of possibilities. And you rest in the knowledge that cosmology, at its heart, is not about predicting the universe's end but about understanding its nature, its laws, and its long journey through time. You begin with a quiet thought. The universe is expanding, and not just steadily, but at an accelerating pace. To understand this, scientists must measure both distances and velocities of faraway galaxies with extraordinary precision. You follow their reasoning gently, aware that each data point, Each photon captured by telescopes is a record of history stretching across billions of years. Your attention first rests on the Hubble constant, denoted as h. It measures how fast galaxies recede from one another per unit distance. Imagine a galaxy 1 million light-years away. Its speed of recession, multiplied by the Hubble constant, gives a precise measure of cosmic expansion at the current time. The value of h sets the scale for the entire universe, linking distance and velocity in a simple, testable relationship. You let this concept settle slowly, appreciating how such a straightforward idea can describe the motion of billions of galaxies. But measuring h is not simple. Light must travel across immense distances, and along the way it interacts with cosmic dust, gravitational fields, and the expansion itself. Astronomers use standard candles, objects of known intrinsic brightness, to calibrate distances. Type Ia supernovae serve this role beautifully because their peak luminosity is remarkably uniform. When these explosions occur, their apparent brightness tells you how far they have traveled. Comparing this distance with the galaxy's redshift, or the stretching of its light waves, allows scientists to infer the expansion rate. You imagine the careful process of observation. Telescopes across Earth and in space track supernovae over months, capturing minute changes in brightness. Data is cross-checked, corrected for extinction caused by interstellar dust, and compared with nearby calibrators. Every measurement has an associated uncertainty, a margin of error that scientists quantify and analyze. You sense the patience behind this effort, the repetition and care required to ensure that the numbers reflect reality rather than artifacts. Another method complements supernova observations: baryon acoustic oscillations, or BAO. These are subtle ripples in the distribution of matter from the early universe, frozen into the large-scale structure of galaxies. You picture the early universe as a hot plasma, where pressure waves traveled through the photon-baryon fluid. As the universe cooled and photons decoupled from matter, these waves left an imprint, a preferred scale in the clustering of galaxies. Measuring the distance between galaxy clusters across the sky allows scientists to reconstruct the expansion history. You follow this with calm attention, noting how patterns imprinted billions of years ago can reveal the current state of the cosmos. You also consider the cosmic microwave background, CMB, the afterglow of the universe's infancy. Tiny temperature fluctuations encode information about the density, geometry, and expansion rate of the early cosmos. By observing the CMB with satellites like Planck or WMAP, astronomers extract data on the initial conditions that shaped the universe's growth. When this information is combined with supernovae and BAO measurements, a coherent picture emerges. You feel the subtle harmony of multiple methods converging to reveal the same story. Yet, even with these sophisticated techniques, small uncertainties remain. Different methods sometimes yield slightly different values for h, a tension that has intrigued cosmologists. Local measurements using supernovae may indicate one rate, while early universe measurements from the CMB suggest another. You observe how scientists treat these discrepancies with care, checking for systematic errors, recalibrating instruments, and considering alternative explanations. The universe, it seems, does not yield its secrets easily. You follow the practical steps of measurement in your mind. A supernova explodes. Its light is captured, digitized, and analyzed. A galaxy's redshift is measured by splitting its light through a spectrograph, noting the precise displacement of spectral lines. Distances and velocities are combined, producing data points that gradually map the rate of expansion. Over thousands of observations, patterns emerge, revealing that the universe's expansion is not constant, but accelerating. You notice how the results depend on assumptions as well as observations. Cosmologists must account for the density of matter, the contribution of radiation, and the influence of dark energy. These factors affect how distances change over time and how light travels through spacetime. You realize that every number, every plotted point, is the outcome of careful modeling, testing, and refinement. The process is methodical and slow, perfectly suited for the long timescales over which the universe itself evolves. You also consider the significance of error bars. Each measurement has an uncertainty, a small range in which the true value might lie. Scientists combine many measurements to reduce this uncertainty, calculating confidence intervals that reflect how reliable the results are. You appreciate the humility in this practice. Even with precise instruments, there is recognition that the universe is vast, complex, and sometimes subtle in its behavior. Through these observations, a clear trend emerges. Type Ia supernovae indicate that distant galaxies are farther away than expected in a decelerating universe. BAO measurements align with this conclusion. The CMB provides a baseline from the early universe, showing that expansion has accelerated relative to predictions without dark energy. Together, these independent lines of evidence build a compelling case for an accelerating cosmos. You feel the quiet power of this convergence, a testament to the rigor and patience of modern astronomy. You reflect on how small changes in the Hubble constant can lead to very different projections for the universe's future. A slightly higher value suggests a faster expansion, while a slightly lower one implies slower growth. Over billions of years, these differences amplify, shaping scenarios ranging from gentle acceleration to extreme outcomes like the Big Rip. You realize that cosmology is not about immediate effects but about understanding the slow evolution of spacetime across immense durations. You notice how instruments continually improve measurements. The James Webb Space Telescope, alongside ground-based observatories, observes fainter, more distant supernovae, and maps galaxies with higher precision. These improvements help refine estimates of the expansion rate and constrain the properties of dark energy. You appreciate the patience behind each incremental advance, understanding that cosmology is a science of accumulation. One observation at a time, building a coherent understanding of the universe. Finally, you think about the philosophical calm of these findings. Even though the universe expands faster than expected, this acceleration does not affect your immediate environment. Solar systems remain stable, galaxies hold together, and planets continue orbiting their stars. The acceleration is a property of spacetime itself, noticeable only over enormous distances and timescales. You sit with this, absorbing the gentle truth that the universe operates on rhythms far longer than any human lifetime, and that science allows us to perceive these rhythms with clarity. You rest in the knowledge that the universe's expansion is measured, not imagined. Every distant supernova, every pattern in galaxy clustering, every subtle fluctuation in the CMB contributes to a growing understanding. Dark energy is inferred through these measurements, its influence tracked across billions of years. The cosmos unfolds methodically, patiently, and you watch, grounded in evidence and observation. And as your mind settles, you feel a quiet readiness to follow the path further, toward models that explore what accelerating expansion might ultimately mean for galaxies, stars, and even the structures within atoms, stretching the imagination only as far as mathematics and physics allow. You begin by imagining a universe in which dark energy grows steadily stronger over time. This is not a world of sudden explosions or drama, but a slow, mathematically predictable evolution, unfolding across trillions of years. The Big Rip scenario arises from this possibility, where the repulsive force of dark energy eventually overcomes every binding force in the cosmos. You breathe deeply, letting the quiet precision of these predictions settle into your mind. At first, the effects are subtle. Galaxy clusters, the largest gravitationally bound structures, begin to feel the influence. You picture two neighboring clusters, separated by millions of light years, slowly drifting apart faster than gravity can pull them together. Over immense stretches of time, their gravitational attraction weakens in comparison to the accelerating expansion. The universe remains calm in human terms, but the large-scale structure is gently reshaped, with clusters gradually becoming isolated islands in a growing cosmic ocean. Next, individual galaxies start to drift. Stars within each galaxy remain bound by gravity for a long time, but the space between galaxies stretches more rapidly. You observe this process with measured attention. The distances between the Milky Way, Andromeda, and other neighboring galaxies grow steadily. Within each galaxy, gravity continues to dominate, preserving stellar orbits and the familiar organization of stars. Dark energy acts on scales far larger than the size of a galaxy, leaving local systems intact for now. You focus on our own Milky Way, imagining its spiral arms and central bulge. For trillions of years, the stars continue their paths around the galactic center, largely unaffected. Yet the light from distant galaxies begins to fade from view as their recession accelerates. Observers in any galaxy would eventually see fewer neighbors, as expansion pushes them beyond the cosmic horizon. This realization provides a quiet, reflective understanding. Dark energy reshapes the observable universe gradually, one distance scale at a time. As time progresses, dark energy's influence intensifies. Galaxy clusters fragment, and individual galaxies drift apart. The scale factor of the universe, a measure of cosmic expansion, grows exponentially. You trace this growth slowly in your mind, appreciating the regularity of the mathematics. The expansion is predictable, yet the sheer distances involved make the process imperceptible over human timescales. Even with trillions of years passing, structures like galaxies persist locally, held together by gravity. Eventually, the acceleration reaches the scale of solar systems. You imagine a distant epoch, far beyond any human experience, when dark energy's repulsive force becomes comparable to the gravitational pull of stars on their planets. Orbital stability falters, planets drift away from their stars, and the familiar architecture of planetary systems unravels. Calculations show that this would occur in a smooth, continuous manner, determined by the exact value of the equation of state parameter W. The process is gentle in progression but absolute in eventual outcome. You reflect on the sequence of events. First, clusters separate, then galaxies, then star systems. Each step corresponds to specific thresholds in the evolving scale factor. The timeline depends on the magnitude of dark energy's density increase. The mathematics provides clear markers, illustrating how acceleration gradually overcomes each type of binding force. You absorb the calm precision of these models, noting that the unfolding is entirely determined by physics, not imagination. Beyond planetary systems, the next stage is even more extreme. Dark energy eventually reaches a level where it can overcome molecular bonds, separating atoms from one another. You consider the fundamental forces: gravity, electromagnetism, and the strong nuclear force. Each force has a characteristic strength, and each resists disruption. Calculations show that only an extremely rapid, persistent acceleration could overcome these forces. The Big Rip scenario predicts that this would happen only at the final stages, long after stars and planets have disintegrated. You dwell for a moment on atomic structure. Electrons orbit nuclei due to electromagnetic attraction, and nuclei themselves are bound by the strong force. These interactions are far stronger than gravity on small scales. Yet in a universe where dark energy's density continues to rise, even these forces can be challenged. The mathematics of the Big Rip allows physicists to predict when atomic cohesion might fail. You feel a quiet awe at the precision of these calculations, showing how fundamental physics applies consistently across scales, from galaxies to subatomic particles. Time stretches forward, almost inconceivably. Billions, trillions, and eventually quadrillions of years pass. Dark energy continues its work with relentless consistency, pushing apart every structure. The universe becomes increasingly empty, as all bound systems dissolve sequentially. Observers, if any existed, would witness a gradual dimming of the cosmos, not in sudden flashes, but as a slow fading of complexity. You reflect on the patient and predictable nature of this evolution, guided entirely by measurable physics. You consider alternative values of W, the equation of state parameter. Slightly different numbers produce slightly different timelines. If W is closer to -1, the sequence of events stretches even further into the future. If W is significantly below -1, the same stages occur sooner. You imagine a family of possible timelines, each one arising naturally from a single mathematical variation. This flexibility does not make the scenario uncertain in principle. It simply shows the sensitivity of cosmic evolution to dark energy's properties. Through all these stages, the universe remains orderly on small scales until the final moments. Stars orbit centers, planets rotate around stars, atoms remain intact. Expansion is relentless but acts most strongly across vast distances. The gradualness of the process allows you to follow it logically, step by step, without imagining sudden destruction. You notice the calm rhythm in this story. A series of thresholds crossed quietly over unimaginable spans of time. Finally, you imagine the very last stage, when dark energy's density has grown to dominate all interactions. At this point, even atomic forces cannot resist. Matter itself becomes unbound. Molecules dissolve, atoms separate, and subatomic particles drift apart. This is the ultimate horizon of the Big Rip, a limit where conventional structures of matter no longer hold. The mathematics describes it precisely, without exaggeration, as the endpoint of an accelerating universe governed by a specific form of dark energy. Yet, even in considering this distant future, you feel calm. The timeline is immense, and the steps unfold sequentially, never abruptly. The Big Rip is not an event experienced in a human sense, but a framework for understanding how dark energy could influence cosmic evolution. You dwell on the clarity of the physics, the way each stage can be traced through calculations, models, and well-established equations. The universe operates according to principles that remain consistent across vast scales and times. You let your mind settle on the pattern. Clusters separate first, galaxies second, solar systems third, atoms last. Each transition is tied to the changing balance between gravitational and repulsive forces. The sequence reflects the natural order of the universe as predicted by general relativity and cosmological equations. You notice the quiet satisfaction of following this logic, the comfort in knowing that the cosmos can be understood through precise observation and reasoning. Finally, you reflect on the broader lesson. The Big Rip scenario, though extreme, teaches you about sensitivity and balance in the universe. Slight variations in dark energy's properties lead to dramatically different futures, illustrating the importance of careful measurement, observation, and modeling. The cosmos, vast and patient, reveals its trajectory only through diligent study and mathematical rigor. You sit with this knowledge, feeling both the enormity of time and the clarity of scientific understanding. And as your thoughts linger on these distant futures, you feel a gentle awareness of the balance between forces. Gravity, dark energy, and the fundamental interactions that hold matter together. This balance, shifting slowly over incomprehensible timescales, shapes the cosmos with precision and predictability, inviting contemplation of both its immensity and the subtlety of the laws that govern it. You begin by contemplating the delicate balance that governs the cosmos. Gravity, the force that pulls matter together, operates alongside the expansion of space driven by dark energy. On small scales, gravity dominates, keeping stars bound in galaxies and planets tethered to their suns. On very large scales, dark energy slowly pushes objects apart, accelerating the expansion of the universe. You settle into this interplay, appreciating the measured rhythm of competing forces. You start with galaxies. Each galaxy contains billions of stars, gas, dust, and dark matter. Gravity pulls these components together, creating an intricate balance between centrifugal motion and mutual attraction. Stars orbit galactic centers along predictable paths, and galaxies themselves form clusters held together by the combined mass of visible matter and dark matter. Even as space expands on cosmological scales, this internal gravitational cohesion preserves the structure of each galaxy for extremely long periods. You notice the calm precision of these arrangements, grounded entirely in physics. On the scale of galaxy clusters, gravity is still significant. The Milky Way, Andromeda, and neighboring galaxies are part of the local group. Dark energy is present, but gravitational binding ensures these galaxies remain in proximity. You imagine the vast distances between clusters stretching, while within clusters, galaxies orbit each other and their dark matter halos maintain cohesion. This highlights a key principle. Expansion is not uniform in its effect. It acts most strongly over regions that are already low in density, leaving high-density areas relatively unaffected. The contrast is subtle but fundamental. You consider planetary systems next. Within a star's gravitational influence, planets maintain stable orbits. The sun's pull dominates the solar system, far outweighing the gentle repulsive effect of dark energy. You follow the precise calculation. The acceleration caused by dark energy is orders of magnitude smaller than the gravitational forces binding planets to their stars. Even on scales as small as our solar neighborhood, expansion is present mathematically, yet practically imperceptible. You appreciate the quiet reassurance that local systems remain intact while the universe as a whole continues its expansion. Moving upward, you examine galaxy clusters again. Dark energy slowly accelerates the distance between clusters that are not gravitationally bound. Over billions of years, isolated clusters drift apart, leaving voids that expand as empty space grows. You notice the interplay. Gravity acts as a counterbalance locally, while dark energy acts as a driver on cosmic scales. The result is a layered hierarchy. Tightly bound systems resist expansion, while loosely bound or isolated structures feel it more strongly. The universe demonstrates this balance naturally, without abrupt disruption. You reflect on the mathematical description. In general relativity, the Friedmann equations govern cosmic expansion. The density of matter and the pressure of dark energy determine whether expansion accelerates or decelerates. If the density of matter dominates, gravity slows expansion. If dark energy dominates, expansion accelerates. You notice the elegance of these relationships, how they predict the growth of distances between unbound structures, and how they preserve the integrity of bound systems. The equations themselves carry a calm precision. You visualize hypothetical variations in dark energy's density. If dark energy were constant, the current balance would persist, with galaxies and clusters remaining intact while space expands around them. If dark energy grows stronger, as in some models of the Big Rip, the balance shifts gradually. Gravity is eventually overwhelmed, first on intergalactic scales, then potentially on smaller scales. You sense the patient rhythm of these processes, unfolding over billions or trillions of years. Each stage is dictated by measurable properties of spacetime, energy density, and mass. You consider star clusters within galaxies. These are tightly bound groups of stars, held together by mutual gravitational attraction. Dark energy is present, yet its effect is negligible here. You understand that the force of expansion acts on volumes of space far larger than a star cluster, and so stars within clusters continue their paths as if the universe outside were not accelerating. The interplay is delicate. Only when dark energy grows extraordinarily strong does it threaten to disrupt smaller structures, and this occurs far beyond current observations. The mathematics offers a calm framework to visualize this hierarchy. You also notice the scale dependence of gravitational resistance. The smaller and denser a system, the stronger its gravitational binding relative to the expansion. Galaxies are more resilient than clusters of galaxies, star systems are more resilient than galaxies, and atoms are more resilient than star systems. This creates a natural order of persistence. Dark energy influences the universe broadly, but gravity governs local stability. You reflect on how this balance allows structure and coherence to coexist with cosmic acceleration. You follow a quiet calculation in your mind. The gravitational acceleration of a planet toward its star is many orders of magnitude greater than the acceleration caused by cosmic expansion. You see why planets do not drift away despite the universe's growth. Even within galaxies, the attraction of dark matter keeps stars on stable paths, counteracting any subtle expansion effect. You feel the precision of this balance, a consistency that underpins the stability of cosmic structures over immense timescales. You imagine the interplay on a cosmological horizon. In regions where matter density is low and gravity is insufficient to bind structures, expansion dominates. Galaxies and clusters become effectively isolated. Light from distant objects redshifts, stretching beyond detection. Yet within high-density systems, gravity continues to maintain organization. This demonstrates the layered effect of cosmic forces. Expansion influences the large-scale geometry of the universe, while gravity preserves local order. You absorb this duality calmly, understanding its simplicity and consistency. Finally, you reflect on how the universe demonstrates resilience. Gravity secures stars, planets, and galaxies, while expansion shapes the space between them. The competition is quiet, predictable, and governed entirely by measurable quantities. You notice the harmony in the equations, the way each force operates on its scale, and the way structures survive or dissolve depending on their mass, density, and separation. The universe is vast, but its principles are steady, reliable, and precise. You rest with the understanding that gravity and expansion together determine the cosmic landscape. Bound systems endure while unbound systems drift apart. The slow, predictable tension between these forces allows galaxies, clusters, and solar systems to exist in a dynamic universe, stretching gently across unimaginable distances. This balance sets the stage for imagining the fate of our own Milky Way as expansion continues to shape the cosmos, guiding your attention toward the structures that will persist or eventually dissolve in the far future. You begin by turning your attention to our own galaxy, the Milky Way, a massive spiral of stars, gas, dust, and dark matter. For billions of years, it has maintained a stable structure, its spiral arms rotating smoothly around a dense central bulge. Gravity holds the stars, star clusters, and gas clouds in place, while the surrounding halo of dark matter provides additional mass to maintain cohesion. You feel the quiet steadiness of this system, aware that it represents a balance of forces that has persisted over cosmic timescales. In the context of cosmic expansion, the Milky Way is deeply resilient. Dark energy exerts a repulsive influence across vast distances, but the density of matter within galaxies ensures that gravity dominates locally. Stars orbit the galactic center at predictable velocities, maintaining their positions relative to one another. You notice how these orbits reflect the underlying mass distribution, including the hidden dark matter halo. Expansion occurs between galaxies rather than within them, leaving the Milky Way largely unaffected for now. You consider the galaxy's interactions with neighboring systems. Andromeda, the closest large galaxy, is gravitationally bound to the Milky Way. Calculations predict a collision or merger in several billion years, forming a larger elliptical galaxy. In this scenario, dark energy does not prevent this interaction, because the mutual gravitational pull between the two galaxies overwhelms the expansive effect at such small separations. You reflect on the slow, predictable dance of massive systems guided by gravity and orbital mechanics. Now, you imagine a future dominated by accelerating dark energy, as in certain Big Rip models. Over extremely long timescales, the influence of dark energy becomes comparable to gravitational forces on the scale of galaxies. In this hypothetical scenario, the Milky Way itself could begin to experience subtle distortions. Stars at the outskirts of the galaxy would gradually feel a net outward acceleration as dark energy overcomes the weaker gravitational binding in the periphery. You sense the slow unfolding of this process, a gentle but inexorable shift over trillions of years. The internal dynamics of the Milky Way help resist early disruption. Stars closer to the galactic center remain tightly bound, their orbits dominated by the central mass, including the supermassive black hole. Even as expansion accelerates the separation of outer regions, the inner structure remains coherent for longer. You observe how density and position determine a star's resilience, understanding that cosmic forces act hierarchically, with smaller, denser systems resisting expansion more effectively. You notice the role of dark matter. The Milky Way's halo extends far beyond the visible spiral arms, enveloping the galaxy in a gravitationally binding shell. This halo strengthens the galaxy's structural integrity, keeping stars and gas bound even as the surrounding cosmic space expands. You reflect on the quiet presence of dark matter, invisible yet essential, its gravitational influence stabilizing the galaxy against external acceleration. This demonstrates the subtle interplay of observable and unseen forces in cosmic evolution. You think about star clusters within the galaxy. Globular clusters, tightly bound spheres of stars, orbit the galactic center at various distances. Dark energy's influence is negligible on these small scales, so clusters maintain cohesion. Open clusters, which are less tightly bound, also survive, although tidal forces from the galactic potential cause gradual dispersal over time. You appreciate the multiple scales at which gravity operates, securing both local and large-scale structures against expansion for extremely long intervals. Beyond individual clusters, you visualize the Milky Way's spiral arms. These arms are regions of higher stellar density, organized by the galaxy's rotation and density waves. Stars move along these waves, creating the patterns observed in the visible disk. Dark energy does not disrupt these internal motions, because its acceleration acts predominantly over intergalactic distances. You note the subtlety of the interaction. The galaxy is immersed in an expanding universe, yet its internal order remains intact until extreme conditions arise. You follow the potential timeline of gradual disruption. In a scenario where dark energy increases significantly, the outermost stars would begin to drift away first. Stellar orbits at the edge of the galactic disk could become elongated or perturbed, and stars at the fringe may eventually escape the gravitational pull. You sense the patient mathematics behind this progression, where the transition occurs over timescales far beyond any human or planetary lifetime, allowing the galaxy to retain its identity for eons. You also consider interstellar gas and dust. These components are loosely bound compared to stars, and their distribution could change as dark energy grows stronger. Gas clouds at the galaxy's periphery might slowly expand or disperse, reducing the material available for future star formation. However, the denser central regions retain their composition, including molecular clouds in the inner disk. You notice the delicate balance between internal gravitational forces and the subtle push of dark energy, maintaining galactic integrity until extreme cosmic acceleration occurs. You reflect on satellite galaxies such as the Large and Small Magellanic Clouds. They are gravitationally bound to the Milky Way and follow elliptical orbits around it. In a strongly accelerating universe, the force of dark energy eventually counteracts the Milky Way's pull, allowing these satellites to drift away. The timing depends on the precise value of the dark energy equation of state parameter, W, illustrating the sensitivity of cosmic evolution to measurable physical constants. You absorb the certainty of this process within the mathematical framework of cosmology. You notice the larger picture. As the Milky Way drifts apart from neighboring galaxies, the local group itself remains a gravitationally bound island for an extended period. The repulsive effect of dark energy operates across larger voids, isolating clusters of galaxies rather than destroying their internal coherence immediately. This layered pattern of influence, expansion dominating low-density regions while gravity dominates dense regions, gives you a calm, clear understanding of how cosmic structures evolve differently depending on scale. Finally, you consider the very long-term outcome. In extreme models of the Big Rip, the Milky Way's stars, gas clouds, and dark matter halo could eventually experience disruption, beginning at the edges and moving inward. This process is predictable and gradual, governed by the same physical laws that maintain galactic cohesion in the present. The sequence is determined by mass distribution, density, and gravitational binding, and it illustrates the hierarchical resilience of cosmic structures. You feel a quiet appreciation for the precision of these predictions. You rest with the thought that the Milky Way, for now, is stable, resilient, and deeply ordered. Its stars orbit reliably, clusters remain bound, and dark matter continues its silent work maintaining cohesion. Expansion shapes the universe on larger scales, leaving local systems secure for billions of years. The galaxy is both a witness to the accelerating cosmos and a domain largely protected from its effects, until the final stages of extreme acceleration arrive. As your mind lingers on the Milky Way's stability and gradual evolution, you sense the subtle transition toward the solar system itself. The forces that preserve the galaxy also act within it, keeping planets, stars, and smaller structures in delicate balance, inviting a closer look at the future of our own sun and its orbiting worlds under an accelerating universe. You begin by turning your attention inward, from the vast scales of galaxies to the familiar arrangement of the solar system. Here, gravity exerts a firm control over planets, moons, asteroids, and comets, keeping them in predictable orbits around the sun. Each orbit is determined by the mass of the sun and the distance of the planet, a balance that has persisted for billions of years. You notice the precision of these interactions, and the stability that allows planetary systems to endure while the universe expands around them. In standard cosmological models, the influence of dark energy on the solar system is negligible. The repulsive force acting on interplanetary distances is vanishingly small compared to the gravitational pull of the Sun. Mercury, Venus, Earth, and Mars follow their elliptical paths without any perceptible change. You allow yourself to dwell in this quiet regularity, appreciating the contrast between local stability and the cosmic expansion occurring across millions of light years. You then imagine a hypothetical scenario in which dark energy continues to grow stronger over time, as in extreme Big Rip models. Gradually, the acceleration of spacetime itself increases, eventually approaching the scale of stellar gravitational binding. You follow the calculations carefully. As the scale factor grows, the repulsive acceleration acting on planetary orbits slowly increases. For most of the solar system's life, this effect is insignificant, but far in the future, it begins to compete with the Sun's pull on the outer planets. Outer planets are affected first. Neptune and Uranus, orbiting far from the Sun, experience the weakest gravitational binding. Mathematical models indicate that as dark energy dominates, the orbital velocities required to maintain stable paths become insufficient, and these planets start to drift outward. Their motions become elongated and perturbed, increasingly influenced by the accelerating expansion of space. You observe this progression calmly, noting that it occurs over incomprehensibly long timescales, beyond the span of any civilization. Next, the more tightly bound inner planets face slower effects. Jupiter, Saturn, and eventually Earth and Venus remain in stable orbits much longer. Gravity continues to dominate in regions closer to the Sun, preserving their circular or elliptical paths. You notice the hierarchy in which dark energy affects the solar system. The weaker the gravitational binding, the sooner expansion can influence the object. This principle mirrors what occurs in galaxies and clusters, reinforcing the predictability of cosmic forces. You consider the role of the Sun itself. Its mass and gravitational pull act as the anchor for the planetary system. Even in scenarios of accelerating expansion, the Sun retains its dominance for extremely long periods. You reflect on the calculation. The acceleration required to disrupt Earth's orbit is many orders of magnitude greater than what we observe today. This highlights the robustness of stellar gravitational fields and the relative weakness of dark energy on small scales. You also examine the asteroid belt and Kuiper belt. These smaller bodies are more loosely bound than planets, and they experience subtle changes in response to increasing expansion. While initially negligible over enormous timescales, the repulsive force could alter the orbits of distant asteroids and dwarf planets. You visualize the gradual shifting of these objects, a slow and predictable drift, reflecting the hierarchical sensitivity of gravitationally bound systems to external expansion. You then think about the fate of moons orbiting planets. The Earth's moon, for instance, is tightly bound by Earth's gravity, and this bond is stronger than the Sun's pull at that distance. The moon remains in orbit long after more distant planets begin to drift. Similarly, the moons of Jupiter and Saturn continue their paths around their respective planets, illustrating how gravitational hierarchies persist even in the presence of extreme expansion. The laws of physics maintain local order for remarkably long periods. You follow the sequence of disruption mathematically. As dark energy grows more intense, the balance of forces shifts incrementally. First, objects in weakly bound orbits drift away. Later, even objects closer to the Sun become vulnerable. Eventually, the orbits of all planets become unstable. Calculations show that the precise timing depends on the value of the dark energy equation of state parameter, W. Small variations in this constant produce significant differences in the timeline, yet the underlying physics remains consistent and predictable. You also consider the energy of these orbits. Planetary velocities are initially sufficient to maintain stable trajectories. Dark energy does not add kinetic energy to planets but stretches the intervening space, effectively reducing gravitational binding over long periods. You follow the math. When the repulsive effect becomes comparable to gravitational acceleration, planets begin to drift outward. The process is continuous and smooth, governed entirely by the equations of cosmology, without sudden jumps or discontinuities. You imagine Earth's orbit slowly elongating in response to the expansion. The sun's influence persists, but the gravitational pull is gradually countered by the outward acceleration of space. Over unimaginable timescales, Earth could drift away from the sun, altering its position relative to the habitable zone. This is a slow, methodical process, dictated entirely by measurable physical constants. You notice the calm rigor in this prediction. Every step is calculable, every effect gradual, consistent with the principles of general relativity. You think about tidal forces and their role in orbital stability. While these forces operate on shorter timescales than cosmic expansion, they do not significantly counteract the repulsive effect of growing dark energy. You see that the eventual dissociation of planets is a purely dynamical outcome, arising from the competition between the sun's gravity and the accelerating metric expansion of space. The timeline is long, measured in billions to trillions of years, providing a sense of cosmic patience. You also consider smaller objects like comets and asteroids in the distant reaches of the solar system. They are affected first, as their weak gravitational binding makes them sensitive to the expanding universe. You reflect on how the solar system is organized hierarchically. Weakly bound bodies yield to expansion earlier, tightly bound ones later. The process is gradual, sequential, and entirely predictable within the framework of cosmological physics. Finally, you imagine the ultimate stage. If dark energy continues to grow unchecked, all planets, moons, and smaller bodies eventually lose gravitational cohesion. Orbits disintegrate, and objects drift independently through the expanding space. Even the sun, as a gravitational anchor, becomes insufficient to maintain order at extreme distances. Matter itself remains intact, but the organized structure of the solar system is effectively dissolved. You notice the precision of this endpoint, described entirely by equations and cosmological modeling. You rest with the understanding that the solar system is remarkably stable for now, yet subject to the slow, predictable influence of cosmic expansion over extremely long timescales. The hierarchical resilience of planets, moons, and smaller bodies mirrors the patterns observed in galaxies and clusters. The universe is both dynamic and structured, and its evolution can be traced logically from large scales down to local systems, with measurable physics governing each stage. As your mind lingers on the dissolution of orbits and the stretching of planetary systems, you sense the next layer of cosmic order, the fundamental forces that maintain atomic and molecular cohesion. If dark energy continues to accelerate, it could eventually challenge these forces as well, providing a bridge from celestial mechanics to the stability of matter itself. You begin by turning your attention inward, beyond planets and stars, to the very building blocks of matter. Gravity has governed planets, and dark energy may one day overcome gravitational binding, but matter is held together by other forces: electromagnetism and the strong nuclear force. Electrons orbit nuclei due to electromagnetic attraction, while protons and neutrons remain bound in the atomic nucleus by the strong force. These interactions are immensely stronger than gravitational forces at the scale of atoms and molecules, which is why matter appears stable even as the universe expands. In the context of accelerating cosmic expansion, ordinary matter is remarkably resilient. At present, dark energy influences the expansion of space across vast distances, but the tiny scales of atoms, molecules, and even planetary systems experience essentially no effect. Electrons remain bound to nuclei, and chemical bonds hold molecules together. You reflect on the precision of these forces, the way the universe maintains internal structure even as it stretches across incomprehensible distances. You imagine a future in which dark energy continues to grow stronger. In extreme Big Rip scenarios, the expansion becomes so rapid that it eventually competes with the fundamental forces themselves. You follow the calculations. The acceleration of space can overcome gravitational binding first, planetary and stellar orbits second, and eventually the electromagnetic and nuclear forces that hold atoms together. The sequence is slow and predictable, governed entirely by equations, not imagination or conjecture. You focus first on molecular bonds. Molecules exist because atoms share electrons or interact through electrical attraction. The energy required to break these bonds is large compared to everyday forces but tiny compared to the energy scales in the nucleus. As dark energy accelerates the expansion of space between particles, It exerts a repulsive influence that can, in principle, counteract the electromagnetic attraction binding atoms into molecules. In the final stages of a Big Rip scenario, molecules would slowly disassemble as electrons drift away from nuclei. Next, you consider atomic nuclei. Protons and neutrons are bound together by the strong nuclear force, the most powerful interaction in nature on small scales. This force keeps the nucleus intact despite the electromagnetic repulsion between protons. Calculations show that even the strongest expansion would need to accelerate space at unprecedented rates to separate nucleons. The process is extreme, far beyond the current state of the universe, yet it is predictable within the mathematical framework of cosmology and particle physics. You think about energy scales and force strengths. Gravity is the weakest of the forces acting on matter, which is why planets and stars are affected first. Electromagnetism is roughly 10 to the power of 36 times stronger than gravity at the scale of electrons and nuclei. The strong force is even stronger, binding quarks within protons and neutrons. The hierarchy of forces explains why the disassembly of matter itself occurs last, long after galaxies, stars, and planetary systems have been disrupted by accelerating expansion. You visualize the sequence. First, large-scale structures, galaxies and clusters, drift apart. Next, stars and planetary systems dissolve. Then molecules unbind as electrons separate from nuclei. Finally, the nuclei themselves, held together by the strong force, could potentially be torn apart if dark energy accelerates sufficiently. The sequence is gradual, governed by the relative strength of each force and the evolving expansion rate. Each stage reflects a precise mathematical understanding, rather than conjecture or speculation. You consider chemical elements. Hydrogen atoms, the simplest, consist of one proton and one electron. Oxygen and carbon atoms are more complex, with multiple electrons and larger nuclei. As dark energy intensifies, electrons in outer shells are the first to experience separation, disrupting chemical bonds. Atomic integrity persists longer than molecular cohesion because the electromagnetic forces within atoms are stronger than those between atoms. You sense the layered resilience of matter, from molecular to atomic to nuclear scales. You then contemplate subatomic particles. Within the nucleus, quarks are confined by the strong force through a mechanism known as color confinement. To disrupt a proton or neutron requires energy far beyond what exists in current cosmic conditions. Only in the final, extreme stages of a runaway dark energy model would this level of disruption be mathematically possible. You note the precise predictability. Every stage, from galaxy separation to atomic disassembly, is governed by fundamental constants and measurable physics. You also reflect on electrons orbiting nuclei. The Coulomb force maintains the orbital paths of electrons, determining the chemical properties of matter. Even as dark energy expands space, electrons remain bound until the repulsive acceleration matches the electromagnetic attraction. Calculations indicate that this threshold is reached only after all larger-scale structures have already dissolved. The hierarchy of binding forces creates a logical sequence, reinforcing the stability of matter until the very last stages of extreme expansion. You observe the gentle inevitability of the process. Expansion operates continuously, slowly stretching distances between bound objects. On large scales, galaxies drift apart first. Within galaxies, stars remain bound longer, and planetary systems even longer. Molecules are affected later, atoms even later, and nuclear structures last. The timeline is immensely long, spanning orders of magnitude beyond human or planetary lifetimes. You sense the calm orderliness inherent in this predictable sequence. You also notice the precision of modern calculations. Cosmologists use general relativity and the measured value of the equation of state parameter, W, to determine how fast space expands. Physicists apply quantum mechanics and particle physics to calculate the forces binding matter. By combining these fields, scientists can estimate the timescales over which dark energy would affect gravitational, electromagnetic, and nuclear structures. You appreciate the rigor and consistency underlying these predictions, a framework built entirely on observation and theory. You reflect on the role of hierarchy in cosmic resilience. Systems with weaker bindings succumb first, while stronger systems persist longer. Galaxies survive longer than star systems survive longer than molecules, and molecules survive longer than nuclei. This ordered progression allows you to follow the influence of dark energy logically, step by step, rather than imagining chaotic or instantaneous disruption. Each stage has a clear explanation based on measurable forces and physical constants. Finally, you dwell on the ultimate limit. If dark energy continues to accelerate without bound, matter itself could be stripped apart, leaving a universe in which fundamental particles drift freely through expanding space. Yet even this extreme scenario is mathematically defined and entirely consistent with the principles of physics. There is no sudden explosion or randomness, only a slow, predictable unbinding dictated by the relative strengths of gravity, electromagnetism, and the strong force. You rest with the awareness that the forces maintaining matter are extraordinarily robust. Gravity dominates at large scales, electromagnetism binds atoms and molecules, and the strong force holds nuclei together. Dark energy acts across immense distances, gradually challenging these bonds in the extreme hypothetical case. The sequence of disruption is hierarchical, calculable, and grounded in well-established physics. The universe is dynamic yet orderly, predictable yet vast, offering a gentle understanding of how even the smallest scales are integrated into cosmic evolution. As your thoughts linger on the resilience of matter and the subtle power of dark energy, you sense the limits of observation and the uncertainties that remain. Understanding matter's stability relies on precise measurement of cosmic acceleration and energy densities, highlighting the role of observation in defining the universe's ultimate trajectory. This invites reflection on how science continues to refine its knowledge through instruments, data, and careful analysis. You begin by considering the tools scientists use to measure the universe and its expansion. Telescopes, both on Earth and in space, collect light from distant galaxies and supernovae. Instruments like the Hubble Space Telescope, the James Webb Space Telescope, and wide-field surveys provide detailed observations across multiple wavelengths. Each measurement contributes to our understanding of cosmic acceleration, yet each comes with limitations which you explore calmly and precisely. The Hubble constant, the rate at which the universe expands, is one of the key parameters. Determining it requires measuring distances to faraway galaxies and their recession velocities. You follow the method. Astronomers use standard candles, such as type Ia supernovae, whose intrinsic brightness is well known, to gauge distances. By comparing observed brightness to expected brightness, they calculate how far away the object is. Redshift measurements reveal how fast it moves away from us. Together, these observations allow scientists to estimate the expansion rate. However, small uncertainties in measurement introduce variation. Distance indicators can have systematic errors, such as variations in supernova properties or calibration issues in telescopes. Even a tiny change in distance measurements affects the derived value of the Hubble constant. Observations using different methods, such as cosmic microwave background, CMB, measurements versus local standard candles, sometimes produce slightly conflicting values. You notice the precision required. Cosmology is a field where small errors propagate over billions of years and vast distances, influencing predictions about the universe's fate. The cosmic microwave background is another critical observational tool. This relic radiation, left over from the hot early universe, carries information about the universe's composition, geometry, and expansion history. By studying the fluctuations in temperature and density within the CMB, cosmologists infer the total matter density, dark matter, and dark energy contributions. These measurements feed directly into models that predict the long-term behavior of the cosmos. You sense the subtle elegance in how light from nearly 14 billion years ago informs our understanding today. Baryon acoustic oscillations provide additional constraints. These are patterns in the large-scale distribution of galaxies, remnants of sound waves in the early universe. By analyzing the spacing of these patterns, astronomers can measure distances with remarkable precision. Each data point strengthens the framework for understanding cosmic acceleration. Yet every measurement contains uncertainties, whether due to observational limitations, cosmic variance, or calibration of instruments. You notice how these small margins influence predictions over cosmic timescales. Error bars and confidence intervals are central to interpreting data. No single measurement gives a definitive value. Instead, scientists express their results probabilistically. A Hubble constant measurement, for example, comes with a range that represents the likelihood of the true value. Similarly, estimates of the equation of state parameter for dark energy, W, are expressed with uncertainties. You observe how these ranges allow scientists to account for limitations while still making meaningful predictions about the universe. You consider the equation of state parameter, W, which describes the relationship between dark energy's pressure and its energy density. The value of W determines whether dark energy behaves like a cosmological constant, increases, or decreases over time. Current observations suggest it is close to -1, but small deviations could significantly alter the universe's long-term trajectory. The uncertainty in W is a primary factor in whether models predict gradual expansion, a big rip, or eventual slowing of expansion. You feel the subtle tension between known physics and measurement limits. You reflect on observational techniques that refine these measurements. The James Webb Space Telescope, with its infrared sensitivity, can observe distant galaxies and supernovae that were previously inaccessible. Improved calibration, longer integration times, and larger sample sizes reduce systematic errors. Combined with ground-based surveys and gravitational lensing studies, these instruments improve estimates of cosmic parameters. You sense the gradual tightening of knowledge, a patient accumulation of data over decades. Local measurements also provide context. Observations of Cepheid variable stars, which pulsate at predictable rates, help calibrate distances to nearby galaxies. Measuring their brightness accurately allows for better calibration of Type Ia supernova distances. These overlapping methods create cross-checks, improving confidence while revealing subtle discrepancies. You notice how consistency across independent techniques reinforces reliability while exposing areas that need refinement. Even with these advancements, cosmology retains inherent limits. Some distances are so great that direct measurement is impossible, and some processes occur over timescales far longer than a human lifetime. Dark energy itself is only observed indirectly, through its influence on expansion, not through direct detection. These limitations mean that cosmologists work within a framework of probability, always refining models as new data becomes available. You sense the humility of science in the face of the vast universe. You think about the role of simulation and modeling. Numerical simulations of cosmic evolution rely on measured parameters and physical laws to predict structure formation, galaxy interactions, and potential long-term scenarios. Each simulation incorporates uncertainties, such as initial conditions and observational inputs. Comparing multiple simulations helps researchers understand the sensitivity of predictions to these factors. You notice the careful balance between modeling and observation, and the patient way science narrows possibilities without asserting absolute certainty. You also consider the interplay of theory and observation. General relativity and quantum mechanics provide the physical laws that govern cosmic expansion, while measurements provide empirical inputs. When observations suggest potential discrepancies, theorists re-examine assumptions, calibrations, or hidden effects. You follow the process. It is iterative, meticulous, and grounded in reproducible results. This continuous refinement embodies the dynamic yet reliable nature of scientific inquiry. Finally, you reflect on the philosophical implication. Observational limits remind you that the universe's ultimate fate is not a matter of conjecture, but a question of measurement, analysis, and gradual accumulation of evidence. Scientists make predictions with high confidence, yet remain open to revision as instruments improve and data accumulate. You appreciate the gentle rigor of this process, where uncertainty is not weakness but a natural part of understanding the cosmos. You rest with the awareness that the universe is studied through careful observation, precise measurement, and acknowledgement of limits. Instruments like telescopes, surveys, and space-based observatories continue to refine our understanding, gradually reducing uncertainties. Even as the solar system, galaxies, and cosmic structures respond to expansion, the work of measurement ensures that models remain anchored in reality. The patient interplay of observation and theory sets the stage for considering the multiple possible futures that emerge from these precise but imperfect measurements. You begin by stepping back to consider the universe on the largest scales. While models like the Big Rip describe one possible trajectory, there are multiple well-supported scenarios based on current observations of dark energy, matter, and cosmic expansion. Each model arises from measurable parameters, including the Hubble constant, the density of matter, and the equation of state parameter, W. You feel a calm awareness that the universe's fate is a question addressed through precise science rather than speculation. The first scenario is continued expansion under constant dark energy. In this model, often associated with the lambda-CDM framework, the cosmological constant, lambda, remains unchanged over time. Galaxies drift apart gradually, but local structures like star systems and clusters remain intact indefinitely. The universe becomes colder and emptier as the density of matter decreases with expansion. You notice how predictable this outcome is. It is governed by equations of general relativity and the measured parameters of dark energy and matter. You consider heat death, a gradual consequence of continued expansion. In this case, the universe approaches a state of maximum entropy. Stars exhaust their nuclear fuel, galaxies eventually fade, and black holes slowly evaporate through Hawking radiation. Energy becomes increasingly dispersed, and large-scale structures lose dynamism. You feel the slow, inevitable nature of this scenario, which does not involve sudden destruction but rather a long-term equilibration of energy across space. The universe becomes increasingly uniform, quiet, and cold. Another possibility involves decelerating expansion. If future measurements show that dark energy decreases in strength or behaves differently from a cosmological constant, gravitational forces could begin to dominate over cosmic acceleration. In this scenario, the universe might slow its expansion or even reverse, leading to contraction. This potential contraction would unfold over billions or trillions of years, gradually bringing galaxies closer together. You note how such an outcome remains speculative but is grounded in current models that allow for variable dark energy. You also reflect on oscillatory or cyclic models. Some theoretical frameworks propose that the universe could undergo repeated cycles of expansion and contraction, each phase lasting immense periods. In these models, the physical constants and matter distribution may influence the dynamics of successive cycles. While observational evidence is limited, the mathematics remains consistent with general relativity and conservation laws. You sense the gentle logic in these hypotheses. They arise from equations and measurable constants, not from imagination. You consider the role of dark matter in these alternative futures. Its gravitational influence stabilizes galaxies and clusters against expansion in the short term. In models where expansion slows or reverses, dark matter's mass contributes to eventual contraction, providing the pull that could counteract repulsive forces. You notice how dark matter is essential in shaping the geometry and dynamics of the universe on both current and future scales. It acts as a stabilizing factor in many scenarios, influencing whether expansion dominates indefinitely or slows over time. You reflect on the differences between lambda-CDM and other cosmological frameworks. Lambda-CDM, or lambda-cold dark matter, assumes a constant dark energy density and cold, collisionless dark matter. Alternative models may incorporate dynamic dark energy, modified gravity, or additional fields that affect cosmic acceleration. Each model produces distinct predictions for the long-term structure and evolution of the universe. You appreciate that these frameworks provide a spectrum of outcomes, all derived from careful measurement, observation, and mathematical consistency. You then examine the implications for local structures. In all models except the extreme Big Rip, galaxies, star systems, and planetary systems remain largely intact for extremely long periods. The differences lie in the behavior of intergalactic distances and the ultimate thermodynamic fate. Even if the universe continues expanding indefinitely, stars continue to shine for billions of years, and life on stable planets may persist within these local pockets of gravitational cohesion. You notice the reassuring continuity that arises from hierarchical resilience. You consider the timescales involved. Even in scenarios where expansion continues indefinitely, the dissociation of structures occurs on scales far exceeding human or planetary lifespans. Stars burn out, planets orbit their remnants, and black holes gradually evaporate. The universe stretches and cools slowly, giving an almost imperceptible unfolding of change over trillions of years. You sense the patience inherent in these processes, where cosmic evolution proceeds according to calculable laws, free from abrupt or chaotic transformations. You also reflect on observational constraints. Current measurements of dark energy and the equation of state parameter W do not definitively determine which scenario will occur. Error bars allow for slight deviations from a perfect cosmological constant, meaning multiple outcomes remain plausible. Each observation narrows the possibilities, yet no single measurement can completely rule out alternative futures. You appreciate the humility built into cosmology. Predictions are probabilistic, informed by observation, and continually refined as data improves. You think about how these scenarios affect energy distribution. In a universe with continued expansion, energy density decreases as space grows, and the cosmic microwave background cools further. In decelerating or contracting models, energy could become concentrated over time. These differences influence the fate of galaxies, the availability of material for star formation, and the long-term evolution of structures. You notice how fundamental physics governs energy distribution on all scales, shaping the ultimate trajectory of the universe. You also examine the interplay between local and global dynamics. While the universe as a whole may expand or contract, local gravitationally bound systems resist these changes for long periods. Galaxies, star clusters, and planetary systems maintain cohesion due to strong internal binding, independent of the cosmic expansion rate. You sense the elegance of this hierarchical ordering. Expansion dominates on large scales, while local forces preserve structure, creating a stable framework for observers within the universe. Finally, you rest with the understanding that the Big Rip is just one scenario among many, all rooted in physics. Some futures involve gradual cooling and entropy increase, others slow or reverse expansion, and some include cycles or alternative gravitational behaviors. The universe's fate depends on measurable parameters and the laws of nature, not chance or imagination. You notice the continuity and consistency across models. Despite uncertainty, each scenario follows logically from well-established principles and observed phenomena. You conclude with a calm reflection on scientific uncertainty. Observational limits, measurement errors, and the behavior of dark energy all contribute to a range of plausible outcomes. Yet this uncertainty is productive, guiding the development of instruments, experiments, and theoretical models. You sense the quiet progress of science. Each refinement narrows possibilities, strengthens understanding, and provides a deeper appreciation of the universe's complexity and resilience. The cosmos, vast and patient, continues to unfold according to rules that can be observed, measured, and comprehended. As you linger in thought, you feel a gentle awareness of time on the grandest scale. Each scenario, whether infinite expansion, heat death, or contraction, unfolds over billions and trillions of years. The universe evolves methodically, its trajectory determined by measurable forces and constants. This reflection prepares your mind to consider the final perspective. How cosmologists think in terms of tomorrow on a cosmic scale, a time far beyond human intuition, yet defined by the same principles that govern every star, planet, and particle. You begin by contemplating the concept of time itself in the context of the universe. Human intuition interprets tomorrow as a period of hours or days, but cosmologists operate on scales vastly different from daily life. The evolution of galaxies, stars, and planetary systems occurs over millions or billions of years, and the changes predicted by cosmic models extend far beyond the span of human experience. You sense the slow rhythm of cosmic time, measured with patience and precision. The age of the universe, roughly 13.8 billion years, provides a reference point for understanding these scales. Light from distant galaxies takes millions to billions of years to reach us, allowing us to observe conditions long past. This means every measurement is a glimpse into the past, and every prediction projects far into the future. You reflect on how the speed of light and the finite rate of cosmic expansion set the framework for understanding cosmic tomorrow. You consider extreme scenarios like the Big Rip, in which dark energy increases without bound. Even under this model, the timeline stretches far beyond human lifespans or the existence of our civilization. Galaxies drift apart first, followed by star systems, planets, and eventually atoms. Each stage is separated by immense intervals, allowing you to perceive change as a gradual, continuous process rather than a sudden event. You feel the slow unfolding of cosmic evolution, governed entirely by measurable physics. You notice how cosmologists quantify these events using billions of years as units. Predictions about the unbinding of galaxies or the eventual dispersal of planetary systems rely on the expansion factor and the equation of state parameter W. These calculations incorporate the current Hubble constant and observed matter density. You sense the care required to express future scenarios accurately, as even small uncertainties can produce significantly different timelines over such immense durations. You reflect on why human intuition struggles with these scales. The processes of cosmic evolution occur over timespans vastly greater than those of individual experience. Stars burn for billions of years, galaxies rotate and merge over comparable durations, and cosmic expansion unfolds over the age of the universe itself. You feel a gentle awareness that tomorrow in cosmology is a framework for measurement, not a reference to daily or immediate change. Time is relative and cumulative, stretching across the vast scales of space. You think about observational constraints on the distant future. While we can measure current expansion rates and the composition of the universe, extrapolating billions of years into the future requires careful modeling. These models account for known physics, including general relativity, dark energy, and matter distribution, but they remain sensitive to parameters like W. You sense the precision involved in predicting future scenarios. Cosmology balances empirical observation with rigorous mathematical reasoning. You also consider the philosophical perspective embedded in these predictions. Studying cosmic futures encourages a broader understanding of time and existence. Human lifespans are brief compared to galactic and cosmological processes, yet the same physical laws govern all scales. You notice the calm symmetry. The forces binding atoms, the orbits of planets, and the expansion of the universe all obey the same principles. This continuity provides a coherent framework for understanding both the present and the distant future. You examine how uncertainty shapes our expectations of cosmic tomorrow. Parameters like the Hubble constant have measurement errors, and the nature of dark energy is still partially constrained. These uncertainties mean that scientists describe multiple plausible outcomes, including continued expansion, heat death, or scenarios like the Big Rip. You sense that the universe's future is both predictable in terms of physical laws and open to refinement as data improves. Each scenario follows directly from measurable physics. You reflect on the hierarchy of timescales. Local systems like planetary orbits are stable for billions of years, stars evolve over similar spans, and galaxies merge and drift apart over tens of billions of years. Cosmic expansion, influenced by dark energy, occurs over comparable and even longer periods. You feel the patient unfolding of events, where each level, from atomic to planetary to galactic, has its own timescale, yet all are integrated into the broader cosmic story. You consider the observational tools that inform these predictions. Space-based observatories, large-scale surveys, and precise measurements of supernovae and the cosmic microwave background all provide data that constrain models of future evolution. Each observation helps refine the timeline of events, reducing uncertainty and improving predictive accuracy. You notice how modern cosmology blends observation and theory, using both to map a universe whose future stretches far beyond immediate perception. You also examine the cumulative effects of small changes. Minor differences in measured parameters, such as the Hubble constant or the equation of state parameter W, amplify over billions of years. These small variations can determine whether the universe faces gradual expansion, heat death, or a Big Rip. You sense the delicate interplay of observation, calculation, and theoretical modeling that allows cosmologists to navigate these vast timescales with confidence and clarity. You reflect on how this perspective alters the understanding of the present. By studying tomorrow in cosmological terms, you appreciate the stability and order of the universe today. The solar system remains intact, galaxies continue their rotations, and atoms hold together. Observing the forces and structures that persist over eons gives a sense of continuity and resilience, reinforcing that the present is not random but embedded within long-term cosmic dynamics. You then notice the role of predictive modeling in human understanding. Simulations incorporate measured parameters, initial conditions, and known physical laws to explore possible futures. These models provide timelines for the unbinding of galaxies, the cooling of the universe, and the eventual behavior of matter under extreme expansion. You feel a calm assurance that predictions are methodical, grounded in empirical data, and refined over time with each new observation. You also think about the interplay of scale and time. On human scales, change is rapid and perceptible, yet cosmic events unfold over durations that seem almost frozen in comparison. You sense the gentle rhythm of cosmic evolution. A galaxy drifting, a star exhausting fuel, a planet orbiting its star. Each step adheres to the same physical laws, yet the timescales involved inspire a broader sense of patience and perspective. You consider how studying cosmic futures informs scientific thought. Predicting the universe's fate encourages precise measurement, careful modeling, and an appreciation for the hierarchical stability of matter. Scientists measure, calculate, and refine, producing scenarios that span billions of years yet remain rooted in observation and theory. You sense that understanding these distant futures provides insight into the present, highlighting the coherence and order of the cosmos. Finally, you rest with the realization that tomorrow in cosmology is measured in eons, not days. Even in extreme scenarios, the evolution of galaxies, stars, planets, and atoms is gradual, predictable, and mathematically defined. You notice the calmness in this long-term perspective, where time stretches across scales beyond immediate perception, yet each moment follows physical laws. The universe evolves methodically, its trajectory shaped by measurable forces and constants. You close with a gentle awareness of your place in this expansive timeline. The universe continues to expand, structures persist, and matter remains bound. Studying cosmic futures enhances your understanding of the present, reinforcing the continuity and order that govern every scale. The patient unfolding of galaxies, stars, planets, and atoms offers a quiet, reflective view of time itself, inviting a deep appreciation for the slow, predictable rhythm of the cosmos.